second compound will be 2hexene. And opposite is there will be 3hexene. So pretty much what you learn for naming alkanes and how to name alkanes, just extend this to alkenes. Just use a number to indicate the location of the double bond. Now, the double bond is special. It gets to have the lowest number. Okay? The other groups, the halogens and the methyl, ethyl, propyl groups, too bad. They get short shifted. The double bond gets to be the lowest number. So, if you have something like this, a double bond here, and say a bromine here, and a methyl group here, too bad. You don't get to be number one over here. This has to be number 1, 2, 3, 4, 5, 6. So the double bond gets priority when you're naming. Even though you got a bunch of groups piled up over here, typically you would start over here. No. So this is a hexene. It's a 1-hexene. And in position 5, we have a bromo group. And in position 5, we have a methyl group. So if you nail down naming alkanes, then naming alkenes are pretty straightforward. Just change that A ending to E and use a number, if necessary, to indicate the location of the double bond. Okay? Now, the general formula for linear alkenes is CnH2n. See how it's different than from alkanes? Okay. So these alkenes there that have 6 carbons, I know I'm going to have 12 hydrogens. And remember, carbon has to have a total of 4 bonds to it. Okay. So that's the general formula of an alkene, CnH2n. Now, you don't need numbers if it's unambiguous. Obviously, you don't need to say, by the way, this compound we call this combination is ethylene. But what would the scientific name be? Nobody calls it that. What would this be called? These are all hydrogens. This is an alkane. This would be ethane. So this would be ethane. Just change the A to an E. And you don't need a number. You don't need to say 1 ethane because it can only be in position number 1. The same if you have 3 carbons, I can put the double bond on the left or the right. It's the same molecule, whether the left or the right. So everybody calls this propylene, but the scientific name is propene. And strictly speaking, you don't need a number. Okay. Now when you get to 4 carbons, then you need a number. You could have a double bond here, or you could have a double bond here. So you can have 1 butene, or 2 butene. So that's when you start needing numbers. If you have 4 more carbons, then you can put the double bonds in different locations, get different compounds. That's when you need to start worrying about numbers. All right, now remember this. If you only have 1 group on a ring, you don't need a number. Right? You don't need to say 1 methyl cyclohexane, just methyl cyclohexane. And the same is true if you have a double bond. That's considered a group. You don't need to say 1 cyclohexene, just cyclohexene. But you know if you have more than 1 group on a ring, then you need numbers. See? So then you have to call this carbon 1, carbon 2. Now it's a little tricky with rings. You always have to count through the double bond to get to the other groups. You have to. So you can't call this carbon 1. this is the way, the powers to be decided. This has to be carbon one, you've got to count through the double bond. Okay? Doesn't make sense, but that's the way it goes. So, and you don't need to indicate the position of the double bond in the ring. That is special. That gets to be number one. Okay? So you don't need to say this is one cyclohexene. All you need to say is 3-methyl cyclohexene. And you might say, where's the double bond? Well, it's in position number one. It gets to be in position number one. Okay? It's special. So double bond in a ring, you're not going to need a number. It is in position number one. And then you got to count through the other. You got to count through the double bond to get to the other groups. So if you remember that, you're good. All right, now we got to talk about cis and trans. You know, we've done cis and trans before. We've only done simple cases where there's no ambiguity. But let me show you a case where it can be ambiguous as to what is this cis or trans. So we have to do some finagling here. This is clearly trans butene, trans 2-butene. This is dividing the okay, and this is clearly cis 2-butene. But what we call something like this, let's dress it up a little bit. Let's put a C string here, and let's put bromine here, and let's put a chlorine here, and fluorine. So what is it? This is a trans. See, it's not clear. So chemists had to come up with some kind of rules to decide is this cis or trans. So look at the two groups attached to carbon and assign a priority. Look at the atomic number of the group directly attached to this carbon. A carbon is attached to this carbon. It has an atomic number of 6. A bromine is attached to this carbon. It has a carbon number, atomic number 35. So these two groups, this guy has a higher priority. Then do the same with these two. Fluorine is atomic number 9. Chlorine is atomic number 17. So these two groups, this has a higher priority. So you would then call this, you know, 1, 2, 3 carbons, right? So this is propene. You get 3 carbons. 1, 2, 3. Carbon number 1 is this guy. Carbon number 1 has a chlorine and fluorine, so you could say 1 chloro. 1, bromine's named first, but not too bad. 1 fluoro. And then, of course, 2 bromo, so we put that first. B comes first. What a mess. So 2 bromo, 1 chloro, 1 fluoro, propene. And since it has 3 carbons, I don't need to say what, you know, it's got to be position 1. Now, so this would be called, the big groups are on opposite sides. So chemists will be lazy and call this trans, but they don't, strictly speaking, they don't like to use that notation. So they'll call this N, and they'll just use E. So they'll call it E, 2 bromo, 1 but chemists will call it trans. It means the same thing. Strictly speaking, they don't want you to use that notation. If it's ambiguous like that, they want you to say Eve. This is German for Entgen, means across from. See? So this would be the Eve isomer. Okay? And let's flip this. Let's leave this guy alone. But let's put the fluorine up here and the chlorine here. Now remember, these two groups here, this has the higher priority. Of these two groups here, this has the higher priority. So this would be called Z for Zusammen, which means on the same side as German. Germans came up with this notation. Z, 2-bromo, blanking. Well, I would accept cis. So when you see Z, think cis. When you see E, think trans. Chemists kind of use it interchangeably. So I'll accept either answer. Okay. So if I give you that structure, I might say the top structure, is that the cis or the trans isomer? Okay. Or is it the E or the Z isomer? Yes.
Is there a reason why you think the methyl group out of
Name it. Out of what now?
for the top?
Oh,
name?
well, it's not really a methyl group. It's part of the chain. See? So it just looks like see, it's a 3-carbon chain. I just want to stick something out there. So you always find the longest continuous chain has the carbon-carbon double bond. That's your backbone. All right, so just, be able to, if you see something like we had earlier, it's obvious that this is cis and this is, if the groups are the same across from each other, it's a no-brainer. But if you have all these groups across from each other that are different, well, it gets to be messy. So then you got to assign. Now remember when you had to assign priorities to tell if something is R or S, when we had to play that game for stereoisomers. So it's the same set of rules. Same set of rules for assigning configuration R and S. If you want to assign cis and trans or Zusammen or Entgen, use those same rules. And we're not going to get carried away. They have some crazy examples. Don't worry about the crazy examples. We'll stick with straightforward examples. All right, so you're excellent in naming these things. The other thing is stability. These alkenes, and they give you, they're not really sure why. They have a couple of different reasons, but chemists aren't really sure. But the more R groups you have attached to the carbon that's double bonded, the more stable it is. Okay. So the least stable alkene is actually acetylene. The more carbons you have attached to the carbon that's got double bonds, the more stable it is. So here I have one. Now what is this? This is the rest of the molecule. It could be methyl group, ethyl group, propyl group, it could be anything. Just a hydrocarbon fragment that's not going to react. It's just going to be there. It's going along for the ride. Okay, so this is going to be monosubstituted. This is disubstituted. You could have disubstituted this way too, though. Let's see if I have enough room to write it. Maybe. This is also disubstituted. Okay. You have 2 R groups total. Okay. And this is disubstituted trans. We have disubstituted cis. This is not neither cis nor trans. Then you try substitute this tetrasubstitute. So the more R groups you have to the carbon that's double bonded, and this is important, the more stable that alkene is. So if you have a choice as to where the double bond goes, put it so you have the most R groups on the carbons that are double bonded. Okay, so you just see you have a choice where to put a double bond. When you make a compound with a double bond, it will go so that you have the most highly substituted alkene. This is the most stable. This is the least stable. Okay. So we'll get into that before I do that, let me just tell you, cis isomers typically aren't as stable as trans isomers. Anybody give me a reason why we found migration? This is the cis isomer. Put a hydrogen here and here. Here's the trans isomer. Someone may have said that. Why is this slightly more stable than this?
There's
Steric strain, they're too close together, yeah. So typically, these start to interfere with each other. If they're in cis, so trans is usually slightly more favored, especially if the groups are big, then the trans tends to be a bit more stable. So remember the stability order. That way, if you have a reaction that forms a carbon-carbon double bond, and you're going to see that in this chapter, and you're asked to decide where would that double bond go. You have a halogen. You have a hydrogen here and a hydrogen here. You're going to use a very, very, very large base. Something has a negative charge. This is going to pull off this hydrogen. This will swing in here. This will leave. You get a double bond at the end. Okay? If that happens. Okay? Let's look at the other possibility, though. You know what? I don't have enough board space. So let's just do this. Just make it so you can see it. I'm just going to draw in a few atoms of interest. Okay, a base is going to attack. If it attacks this hydrogen, this pair of electrons will flip up, this will leave. If it attacks that hydrogen there, the product you're going to get will be this. This is how you can make an alkene. Okay? But suppose, let's just say this is pathway A. Suppose the base attacks this hydrogen. And this pair of electrons flips up and this leaves. Well, that would be pathway B, let's say. Pathway B would be this one. So which would be the major product? Path A or path B? Let's see, we have hydrogen here, hydrogen here, hydrogen here, and this is an R group. Here we have a hydrogen here, and a hydrogen here, we have an R group here, an R group here. It doesn't matter how big the R group is, just how many R groups you have. So we just talked about this. The more R groups you have on the carbon-carbon double bonds, the more stable it is. So if pathway A is followed, you get the double bond at the end, you get only one R group. If pathway B is followed, you get the double bond in the middle, you get 1 to 2 R groups. Now you might say, this has 2 carbons, this has 2 carbons. Doesn't matter how big the R group is, it's how many R groups you have attached to that carbon double bond. So this right here is the major product. It's more stable. So get the double bond in the middle of the molecule right at the end. It's favored more if you get it in the middle. Now there's tricks you can do to get it on the end. So we'll talk about some of the tricks. But if you don't put any tricks, it's going to usually go toward the middle of the molecule. It's more stable. All right, now, it's kind of annoying the way chemists do this, but strictly speaking, if something has a lone pair of electrons, it can either be a nucleophile or a base. Okay? If you have something that has a lone pair of electrons and it attacks a carbon, they call it a nucleophile. Doesn't make a name of charge. So if it attacks a carbon, it's labeled as a nucleophile. If it attacks the hydrogen, even though it's the same thing, they don't call it a nucleophile, they call it a base. So in the last chapter, the thing that had a lone pair of electrons was attacking a carbon, they labeled it as a nucleophile. Now they're going to, it's the same stuff, same reagents, but they're going to tag it now as a base if it attacks the hydrogen. So they're basically the same, okay? how do you know if it's gonna attack the carbon or the hydrogen? Well, it does both. So, substitution and elimination compete with each other. I'm gonna have to tell you which reaction is taking place. Okay? This is an elimination reaction, because you eliminate a hydrogen and a halogen. Actually, it's this hydrogen. Okay? So that's why it's called elimination. We don't care about the inorganic products, right? So don't worry about it. Okay? Doesn't matter. And elimination can occur in two separate ways, two mechanisms. Now, they're elimination reactions, not substitution, so they're called E mechanisms. And in one mechanism, the simplest one, two things are involved in the slow step, and that's the only one step, that's it. And what else I gotta tell you? I can't remember. Oh yeah, it's called the E2 mechanism, because it's an elimination and two things are involved. So here is the E2 mechanism. And let's make life easy. Let's just get rid of any clutter that can confuse us. Okay, so if I tell you this is good by the E2 mechanism, then here's what you want to draw. It's one step. Two things involved in the slow step. Okay? And you can guess probably. Attach this hydrogen, close it off. This pair of electrons slips in here, and this here. So that's it. That's all I need. 3 atoms in one step. Okay, what are the 3 dance moves, I guess? Well, it's proton transfer. This is being transferred to this guy. It is, I don't know, loss of leaving group, I guess. I don't know what this is called. Maybe they don't have a name for it. And this is loss of leaving group. So it's a proton transfer, loss of leaving group. Two things that happen. You're not rearranging anything. You don't have a nucleophilic attack. There's no nucleophile here. This is a base. Okay, so it's a proton transfer. And anyway, so that's the E2 mechanism. So what is the rate law expected to be? It's going to be the concentration of the Rx and the base. Okay. So sometimes when you do elimination reactions, it's a second order reaction. Okay. Now these groups have to be pointed in opposite directions. They have to be pointed in opposite directions. That's not a problem. If you have carbon-carbon single bonds, they're free to spin. So I don't care which direction in space it's going on. It's going to happen. Okay? You don't need to worry about it. Okay? Now, the only thing you got to worry about, I guess, is if I ask you for a mechanism, I'm going to give you starting material or product. I'm going to make it simple. Okay? But if I ask you for a particular reaction, we add a base, and you give me a major product. Formed by the E2 mechanism. Now, you have there's a hydrogen here, and there's a hydrogen over here. So it's going to lose. We know it's going to lose a halogen. We know that. And we also know it's going to lose a hydrogen right next door to it. But which one is what you want to figure out? And again, the more highly substituted alkene is the one that's favored. So you have 2 places you could potentially put a double bond. You could put a double bond here, this H and BRB, or you could put a double bond here, this H and BRB. So ask yourself which one gives you the more highly substituted alkene. That's the major product. And of course, hopefully, you put the double bond here. If you put the double bond the other place, this, one way to do this, how many hydrogens are attached to this carbon? See, none. How many attached to this carbon? 1. See? So this first structure has 3 R groups, Here's one, here's another, because there's only one hydrogen. Let's look at this other structure. This structure, this carbon has to have a hydrogen, and this carbon has a hydrogen. So this carbon, this compound rather, is a di-substituted alkene. It's got an R group here and an R group here. See, so this is the major product. So you want to be able to pinpoint that, which is the major product. Now, I'm going to tell you if it's elimination or substitution, they always compete against each other. You always have a little bit of both. See, because what can happen? Besides the guy with the lone pair attacking this hydrogen, and this flipping in, and this leaves, what about this? Suppose this attacks this, it just kicks this out. That will be a substitution reaction. See? So which is it? Well, it's going to be a little bit of both. See? So it's, that's why, again, chemists spend so much time purifying materials. If this attacks the carbon, then they call it a nucleophile. It's attacking the carbon nucleus. If it attacks the hydrogen, they call it a base. Okay? But they both will have a lone pair and a negative charge. So I'm going to tell you, I'm looking for the elimination product. Give me a double bond somewhere. If I tell you the substitution product, then substitute. And I tell you, do we have any control over this? And of course, the answer is yes. Okay. Here's one way you can control this. This makes life simple. Let's use a small base. No, not a small nucleophile. Let's use hydroxide. That's pretty puny, okay? That is going to tend to give you substitution. But let's take a huge base, okay? A huge nucleophile base. Let's take this guy right here. That is going to tend to give you elimination. In order for substitution to take place, you got to get in the face of this carbon. You got to be able to penetrate, get in here and attack this carbon. So if you're small, you can get in there and do that. If you're huge, you're not going to get in there. You're going to hang out on the fringes. You can't get that close to the carbon. So if you're a huge molecule, a huge ion, I should say, you're not going to be able to get into this carbon. Instead, you're going to hang out on the fringes and just pluck off a hydrogen. And you're going to get elimination. So if you get a big, bulky, negatively charged ion, you tend to favor elimination. Because this big, bulky ion can't get in here and attack this carbon and you got the bromine. It's just too crowded. So you can stay outwards and pluck out a hydrogen. If you use a small negative charge from zero, you can get through all this mess and get into the carbon, attack the carbon, and kick out the bromine. So I don't have to tell you though. Okay, I'll say this is an SN2. Give me a substitution product. Okay, so that would be this. But if I give you this guy, I'll probably say give me the elimination product, and that would give me this. Okay? Now I don't care about the other products, just the elimination product. Okay? That's all I care about. The other product would be Br minus and TBU alcohol. So we're going to throw this. See that? See, if I mix this and this acts as a base, it's going to pull off this hydrogen, you can TBU alcohol, and then I'm going to get bromine ion, and I get that, and I get my product of interest. Okay, so focus in on a product of interest, not these throwaways. All right, so that is an elimination reaction. E2, single step, one step. The rate depends on the concentration of the base, we'll call it a base, and the substrate, the victim. Okay? Sometimes the rate of these elimination reactions depends on only the concentration of the substrate. When you do elimination, sometimes this is the rate law. So you gotta invent some other mechanism, of course. And here it is. And this is true if you use a weak base. Like, okay? And I say elimination is taking place, okay? So you get this. How did this happen? The rate law, oh, here's the rate law. It already depends on this concentration. So what happens? This is weak base. It's not going to attack anybody. It's going to wait for this to leave, just as before. And you're going to form in a slow step a carbocation. Then this hydrogen is more easy to leave now. And then your weak base, water. Pull this off, just put it in there, and you get that. That second step occurs fast. So the first one is just loss of leaving group, right? And then proton transfer. Proton was on here, and it gets to CH3O plus, Br minus, and then if you want to, this transfers the proton to bromine, get HBr, who cares, it's water. The final other products, if you start with this, and make this, your other byproducts will be water and HBr. All right, so elimination can occur in two separate steps. How do you know that? Well, sometimes the rate law is that, and sometimes the rate law depends on both. So, and sometimes you get rearrangements. Anytime you get carbocations, you get rearrangements. Now you might say, why doesn't the water attack the carbon? You get substitution. And the answer is yes, it's going to happen. You get a mixture. The water can either attack the carbon, give you a substitution, or attack the hydrogen, give you an elimination. So I'm going to tell you I'm looking for the substitution product or the elimination product, because you have no way of knowing what's going to happen. Now chemists have ways. If you take an advanced organic chemistry, they'll talk about the finer points, how you can manipulate the conditions to get one to favor over the other. One big way is if you use a big, bulky base that tends to favor elimination. It can't get into the carbon and do a substitution. If you use a small base, then you tend to favor substitution because you can get into the carbon. But there's other tricks you can do. Now, there are some serious constraints when you have the E2 mechanism operating. These guys have to be pointed in opposite directions. You have to be for an E2 mechanism. Okay? The base comes in from behind, causes this flips up and flips up. Now, if you have a straight chain carbon, it doesn't matter. There's free rotation about carbon-carbon double bonds. Okay, so it doesn't matter. If you see a ring, then a red flag needs to go up. If you see a ring, you can't rotate about the ring. Everything's locked into position. Okay? So they have to be anti to each other. The groups that leave for the E2 mechanism one must point up, the other must point down. Otherwise, nobody's going anywhere. Okay? And the more highly substituted alkene is always favored. Okay, so, you can go home tonight and practice your drawings, I'm sure. I'm adding a base, strong base, the elimination by E2 mechanism. Can you give me the structure of the product? Now remember, when elimination takes place, one carbon loses a halogen, the carbon next door loses a hydrogen. So you could argue that here's the carbon that's going to lose a halogen, here's the carbon that can lose a hydrogen, here's the carbon that loses a hydrogen. But it makes a difference. Remember, these hydrogens that are leaving have to be pointing in opposite directions. So there really is only one possible product you can get here. There's, again, severe constraints. Remember, the halogen that leaves and the hydrogen leaves, they got to be pointing in opposite directions. Otherwise, they're not going to leave. So, this is the halogen leave. This hydrogen leave, because this is pointing down, this is pointing up. This hydrogen can't leave. It's not going to go. It's got to be, they have to be anti to each other. It's called anti-coplanar. They're all in the same plane, and one is pointing down and the other is pointing up. Okay. So, if you do this reaction, the only product you will get is this, and this is the one here. You get practical artwork, hydrogen here, whatever. That's a group here. I'm going to put BT because I don't have space. And then, I didn't draw that very well. And this group is up and down. I'm not going to be able to worry about it. If you get it perfect like this, I'm not going to. The main thing is, I want to see that double bond between the ethyl group here and this carbon, not the methyl group here. So double bond, as long as you draw something that shows you a double bond, I don't give you any point up or down, I'm not going to put it on. So don't worry about that. So you might have to draw this hydrogen out, I'm not going to take off. Strictly speaking, this is in the plane, all these are in the same plane. Like this. So remember, serious constraints with the E2. If you see a ring, then you got to be careful. If there's an E1 mechanism operating, no problem. Okay. The E1 mechanism, you go. If this mechanism was E1, here's what would happen. You could have formed carbocation. Bromine's going to leave first. Giving you a flat carbocation. Okay. And then in the next step, the base will pull off either this hydrogen or this hydrogen. It doesn't matter. This is flat. This is down, this up. So you can get a mixture. If this goes by the E1 mechanism, you start with this, add a base, and I tell you the mechanism is E1. That's the slow step. And like a shot, you get a form, I'm being sloppy here, you get a form over on here, the CH3, CH2, CH2H, and you have the double bond here. Again, I'm not going to quibble about exactly how you draw it. This is wrong. So this question, I would tell you there's two products. I'll give you the hint. I'll say two products. See? So a lot of times when you get carbocations, you get two products. And double bond go here or here. But with E2, remember, there's severe restrictions with E2. All right, one more point and then we'll call it night. It's just overwhelming the first time you see this. It's just the way it is. Here's the hint. The more highly substituted alkene is always formed. Remember that. sometimes you can specify the mechanism, okay? So adamant base, take your pick, E1 or E2. But I'm only looking for the major product. So there's two possible products you could form, but you want to realize that one product is more stable because it's a more highly substituted alkene. Remember, the more highly substituted alkene is favored. So, I'm not specifying, there's no holes barred here. I'm going to lose a halogen, and next door I'm going to lose one of these hydrogens. Take your pick. It can be anti to each other, or same, it doesn't matter. So the two potential products you can get, you can get the on here. Or you lose this H in this bromine, or you can get on over the other side. And one way to tell which is the major product is to draw in the hydrogens if you want to. Attaching these carbons right here. And those are two potential products. So this carbon has one hydrogen, this carbon has one hydrogen. And an R group and R group, so there's two R groups here. This carbon has one hydrogen, and this carbon doesn't have any. So there's actually three R groups. You see that? So this is less stable because I only have two R groups. Here's one, here's the other. This is more stable because I have 1, 2, 3 R groups. So I only have one hydrogen here. So the major product would be more highly substituted alkene. If there's no other restraints, it's free to go in either direction. In this case, it's free to go, I can only go on here or here. But one will predominate, one will be the major product. Okay? So again, anytime you see rings, a red flag should go up, that you got to pay special attention as to where the double bond goes and which directions in space these guys are pointing to. So we have two mechanisms for elimination, E1 and E2. There's factors that favor one over the other, so we'll talk about that next week. Okay. Before the test next Thursday, I'll be able to answer any last-minute questions that come up, and then we'll take the test. Okay. Good luck. Hang in there. I know it's tough. Thanksgiving holidays around the corner, sort of. So yes. What's that now?